Thank you. Take it away, Cory.
Right. Hi, so I'm Cory and a faculty fellow at the Center for Data Science at NYU. And I'm really happy to be here talking about estimating racial disparities when race is not observed. It's going to fit into a lot of stuff that's been talked about by the other great papers in sessions so far. So I'm going to use one example through our short talk here about supposing you have a data set that's like maybe from like a state voter file where you have people's names, you have where they live, you have some outcome where you care about, in this case, what political party they're registered to. You'd like to understand what fraction of each racial group is, registered with each of these political parties. The problem is we don't have any race information on this file, right? So we want to compute this conditional expectation of this outcome variable on race, but we can't do it. The data's not there. Talking about political parties in this case, this is actually obviously something that crops up all over the place. You see it in voter files, but also in the healthcare setting, financial services, lending, insurance providers. We're actually working with the Internal Revenue Service. They're trying to understand racial disparities and who uses various tax programs and tax code, things, and you don't put your tax, you don't put your race in your tax form, so that's another data set that's not available. So anytime you're trying to do a fairness audit or any kind of evaluation of racial disparities from big data, where you don't have race as a column, you're running into this problem. And so how do we go about producing estimates in a case like this? It's really a two-step problem. The first step is we have to sort of impute this sense of attribute race somehow, and that's a prediction problem. And then once you have these imputations, you have to somehow use the imputations to actually estimate your actual quantity of interest, which is the disparity. Okay, and it's the second step that really has not gotten a lot of attention. People spend a lot of time talking about how we can do prediction or imputation of race, but really not a lot of time spent talking about how to use those imputations in a statistically sound way to make sure we actually can get like a trustworthy estimate of these disparities. And like I said, that first step is really just like classic machine learning in some sense of like we're doing prediction. But a lot of the things people have been implicitly doing for the second step actually leads to bias. And so you can have actually a great, well-calibrated, highly accurate race imputation model. And if you just naively use those outputs to estimate disparity, you can sort of provably end up with disparities that are underestimated. You estimate less of a gap between racial groups than actually exists. So getting the second step right is really important. And that's what this talks about. So in particular, I'm going to quickly introduce this new set of assumptions about how we use these imputations, and that'll motivate a particular statistical methodology we call BIRDiE, which eliminates all the bias. All right. So people have probably heard about this issue of imputing race. The way that people do it a lot is called Bayesian Improved Surname Geocoding. So the idea is we're going to combine two pieces of information that we have in many data sets that are written for race. The first is where you live. Unfortunately, we're very segregated by race in this country. So where you live, that tells a little bit about what race group is. Also, last names. So if someone's named Hernandez, if they live in Texas, that makes it pretty likely they're going to be Latino. Very different from Smith, who lives in Minnesota, perhaps, right? So the Census Bureau actually publishes information on both these variables. It's probabilistic in the sense that we have the probability of belonging to each racial group conditional on your name or your location. So you can just combine those two things with Bayes' rule, and you end up with a set of probabilities for each individual in your data set of belonging to each racial group, conditional on where they live, what their name is. So what people do at this point is where the magic happens. So once you have this probabilistic prediction from your computation model, how do you then use that to come up with an estimate of a disparity? And the easy thing to do is to just sort of threshold these probabilistic estimates. So if someone's 50% plus one, likely to be black, or whatever, you just code them to that category. And now you have a deterministic imputation of every single person in your data set race. you can just go tabulate things and come up with, any disparity estimate if you're interested. Intuitively, we shouldn't like this because you're throwing away all this rich probabilistic information, right? So instead, what you might think is good is use the probabilities as weights. So if someone's 50% likely to be black, 24% Hispanic, 29% white, whatever outcome they have, 0 or 1, you're going to put 50% of that in the black group, 25%, and 25% white. So you take weighted averages of your outcome variable over probabilities of each racial group, and that's going to give you, again, these estimates of disparities or what have you. So this seems really natural, very intuitive, using the probability information. How can this go wrong? Well, it turns out it's actually almost guaranteed to be biased. So this is what it looks like mathematically, but you can show that, like, even if you have infinite data, no sampling uncertainty, taking this approach is actually not going to converge to the disparity estimate you care about. In particular, it converges to something that is about how much your outcome relates to race after you control for where you live and what your name is. What this means is that, like, whatever disparity we're trying to measure, if it isn't completely explained by where you live and what your name is, you're gonna estimate it incorrectly. And obviously, the reason we're estimating these disparities in the first place is because we don't think it's just about where you live. There's race is an important part of that equation. And so basically, look, if there's any actual, like, direct effect of race on the outcome you're measuring, that's not going to get mopped up by these BISG probabilities. It's not going to get measured, and it's going to lead to bias in your disparity estimation. This thresholding approach, where you just sort of like hard assign people to different categories, also biased. You don't have a nice formula for it, but basically both thresholding and weighting, which are the two things people do to use these mutations, do not give you even asymptotically the right answer. The reason for this is that in order for this weighting approach to work, you basically have to believe in a particular independence assumption about what's going on in the data, specifically that whatever your outcome is independent of race after controlling for where you live in your name, right? So again, as I say, like, the reason we're studying racial disparities at all is because we actually think race is an important variable. And for these estimators to work, you actually have to assume that race doesn't matter other than through this channel that goes through where you live, right? So that looks like something like this picture. It's like a causal diagram. Like, race can have an effect on your outcome, but it has to be mediated through only location and surname. And only if this holds will this weighting approach give you an unbiased estimate of disparity. So this is not possible. Sometimes it might be, like maybe you're in a setting where people discriminate on the basis of names alone. It's all they see, job application or something. Okay, now this picture might make sense. But in a lot of things we're studying, that's not the case. Algorithmic decision making, we're using a whole bunch of variables measured from people's the data. It's not going to hold. Great. So what we're going to propose is a different assumption. And if this assumption holds, we'll have a methodology that will give you the right answer. So this is the assumption Bayesian has to make. Race independent of the outcome, conditional on where you live. If instead we're willing to assume that the names are independent of the outcome, conditional on race and where you live, that's going to open up a new path to estimate these things accurately. So to give you an example of this is saying among white voters, white people who live in, let's say, Minnesota, a Smith and a Jones, like knowing if you're a Smith, a Jones, or some other last name, that doesn't tell me any information. That's not predictive of the outcome thing I'm trying to measure. Right. So once I know your race and where you live, your name doesn't tell me anything about the variable I'm trying to measure disparities on. So again, unless you're in some setting where people are discriminating using names, it's actually extremely plausible. Right? We don't usually think of names as having a direct causal impact on the type of stuff we're interested in measuring. Right? So if that's the case, look something like this picture, then you can use our methodology. It's called BIRDiE. It stands for Bayesian Instrumental Regression for Disparity Estimation. It's basically a Bayesian model actually two models, you put them together. So the first model is your BISG model, or really any substitute. So if you have any fancy machine learning method that can predict race in a probabilistic manner, you can use that. And that gives you, you have to get this table of probabilistic estimates, and you put that together with the model you would have liked to fit if you had observed race in the first place. This could be some simple regression, it could be some fancy, other, machine learning technique, but you have this the model you would have liked to fit, and you have this probability thing. And you can combine these together into certain posterior, and you end up with estimates of these disparities that are going to be correct if this assumption I talked about holds. This is a really flexible approach, and that you're not going to be connected with either outcome model. It's like a two-step thing, so you can first focus on predicting race very well, and then you can apply this methodology to use those predictions in a statistically coherent manner. I'll be talking questions about how we do this, but you can just nice ways to compute this using an EM algorithm that scales really well. But I'll just run quickly through the last couple of minutes what this looks like in practice on some actual data. So I motivated this with this example of a voter file. The reason I did that is we actually have a voter file in North Carolina, and we actually observe race. So we actually have a ground truth, and we can actually apply our technique and see how well it works in practice. So we have millions of voters. We have a race, we know where they live, and we have the party reg, and we can create these probabilistic race estimates. You can run it through this new method, and we get a output like this from our software, and then we can go compare. What are the disparities in party registration between racial groups? How close are those to the actual disparities in the file? So I'll show you the difference between white and black voters registering for different political parties. So you want things to be at 0. That would give you exactly got the disparity right. If they're above the line, it means we thought that the gap was too wide, and vice versa. So the circles and the X's are the traditional methods that everyone uses, the weighting and the thresholding. And then our methods here in red, you can see it vastly. So the actual gap between Democratic Party registration between white and black voters is 70 percentage points. We get pretty close to that, but if you use these other methods, they would think it's only 20 or 30 percentage points. So they're really vastly underestimating the size of this gap, and you can get a much better result if you use this kind of alternative methodology. A similar story for Hispanic, white Hispanic disparity estimation. You can show a lot more error, in particular in direct underestimating the size of disparities using these old techniques. I'll sort of skip through this. There's other ways to measure the accuracy. We looked at on those things as well. So the takeaway here, this is because I talked about race. This would also apply the exact same sort of idea. Would apply to trying to measure gender disparities using first names as a proxy. The key thing is whenever you're trying to use an imputed variable to in a downstream setting, you want to run regression with an imputed variable. You want to take averages with an imputed variable. You have to be very careful because measurement error in those imputations can cause a lot of bias. And so even if you have a model that's 98% accurate predictive power and well-calibrated, that can still cause bias because there's still that little bit of residual measurement error, and that can be correlated with things in a very dangerous way. So thinking very clearly about the statistical challenges that poses when you use those imputations in downstream tasks is extremely important, especially if you're talking about measuring important things like racial disparities. So you can check out the software if you like. I can answer your questions. Thanks very much.
Very much, fantastic talk. So we're going to open it up for questions. And just a note, since we're running a little bit late, we're going to expand the breakout session, the break session that we'll have in a little bit, up to 3:45. So just a heads up so that we can continue these rich discussions. So let's open it up for questions. Who would like to ask questions to this great talk? Oh, excellent. Please introduce yourself so we all get to know each other.
Hi, I'm Abraham Dale. I'm a PhD student at Rutgers. So I want to kind of interrogate that assumption that names are unrelated to voting records. I think that is true in some cases. I think you have to be very careful with it because in certain populations, it's not very true at all, especially when there's strong religious influence on both name and voting records. which is, so even once I know your race, like India, whether you're Hindu or Muslim, it's gonna have a huge impact on how you vote. And that's not gonna be, and that's going to kind of break this assumption, and that will be captured quite possibly in there. And will, and in that sense, even once I know your race, knowing your name helps me a lot, that I could vote.
Yeah, so it's a great point. These assumptions are never exactly met, and so we have a paper you can get on the link, but we do go into like ways you can sort of weaken this assumption, like control for additional things. So like we use some 1930 census data that we had was like individual records we can see if it's old enough, and it's tied to like place or like country you were born in, like very detailed. So we can use that to actually like come up with like an even more specific measure of the name, race relationship and control for some of these things. And then you can do some stuff. It's a very good point.
I still think religion is going to be hard. It's not connected to census data, and like even like New York City, whether you're Jewish, it's going to affect how you vote. And that is very much correlated with your name and not at all correlated with your race, really. These people will all be coded as white, and they will all possibly born in the US, and yet their religion tells people a lot of what their name has to do.
Yeah, but then again, like those last names, for example, have like distinct immigration histories. If you look back at when people with this name, when did they come in? Like there's data we can collect on that. You can actually control that. And then talk about that. So it's very cool things you can do. Yeah, it's definitely worth interrogating that section.
Thank you. Please introduce yourself.
Hi, Michael, third year PhD student at Carnegie. So I just want to double check some of your intuition and see if you've also thought about this issue. But so to me, when I was looking at the two approaches that result in bias estimates, I was thinking that a third approach would be to and kind of do a blend of the two approaches. So when you get a probabilistic estimate, you can apply hard thresholding but treat your probabilities as a distribution you can sample from. So like if it's 70% black and 30% white, you can sample like 70%, it would be like a 1. Does that basically reduce to the same weighting problems that you get in the long run? I just wanted to.
Yes, so the question is basically this is like a multiple computation approach. If I sample from these probabilities that many times, like if you ask this, what happens? So it's basically multiple computation. And if you just do that naively, it reduces like you get the exact same with the weighting estimator. And the reason for that is like anyone's worked with multiple computation before. When you do a multiple computation for missing data, you have to your missing data model has to include all the relevant variables. And so the outcome variable is very important. It's not getting brought into that multiple computation procedure. You can actually use our methodology to do that multiple computation because we're bringing in the outcome variable and jointly modeling the relation of the outcome variable and race. Then you can actually trust those multiple computation estimates. Yes, very good point.
Yeah, thank you.
Thank you very much. Do we have any? Oh, we have another question. Excellent. Please introduce yourself again.
Cheers, thank you. Yeah, I'm still Karen Ashton from the Turing in the UK. Thank you for this really wonderful talk. My question is kind of along the lines of the first question. The example I had in mind was something like so not BISG, but approaches that use first name as well as surname. And let's say we're predicting you're predicting race. So of course, if you use first name as well, then if you have something that has a gender bias, then you might be hurting your assumption. But then on the other hand, if you also include first name, you have a bit more predictive power, and so you might be better at predicting race. So I guess if you wanted to use this in a practical scenario, how do I think about whether that's going to help or hurt, or do I just need to test it?
Yeah, that's a fantastic question. So yeah, this is one reason I've been a little skeptical, and I talk to a bunch of practitioners who do this. First names are tricky, they're not inherited as much, and so it's just like even within a racial group, first names have very strong class stables, right? That can really correlate with these things, and there's of course like the gender issue there. So the way I think about this is obviously when we do predictive ML, whatever, we're very focused on maximizing accuracy. That's not really what you want in this setting. So if you let me pick between two racial imputation models, one is not very accurate. It's like 51%, 49%, but it's extremely well calibrated. And that when it says the probability of being white is 51%, it's exactly 51.0%. That's model one. And model two is like 95% accurate. The probabilities are kind of off. Model 1 is going to be much better estimates of racial disparities. It's just statistically trustworthy. Model 2, even though it's pretty accurate, even the little is left can really cause a lot of bias. So it's the same like data. I would take small, high quality data set over a large biased data set. It's the exact same idea. A inaccurate but well-calibrated model is much more useful for something like this than a highly accurate but potentially uncalibrated model. So if you can actually if you can just strip out data and make fewer assumptions and have better calibration properties, that's actually going to give you much more reliable results than throwing in stuff to increase predictive accuracy, even when assumptions might be met. So yeah, that's my 2 cents, but hope that's helpful.
That's really helpful, thank you. So in the specific example I asked, probably the right thing to do is not to use first name as well.
Yeah,
Thank you.
yeah, thanks.
Thank you. Do we have any other questions? Fantastic discussion. So let's give ourselves another round of applause.